Ooh, YouTube can see me again. Okay, good. Can the Twitch people see me? For some reason, my streaming provider decided to just get rid of YouTube integration entirely. It's not true. I just had to add it back, but the audio is choppy. That's interesting. That might just be because I just started it up. Choppy audio. It's laggy. That seems like a problem that we should try to fix. Let's see here. So that's set up that way. Super choppy. And now it's better? I didn't actually change anything. Well, it looks like the bitrate to the server is stable. There's echo now. Good. Love to hear that. Is there still an echo? Or is the echo gone too? Okay, now, great. Okay, so the solution was just wait until it fixes itself. Fantastic. Okay, so just to like reset now that things have been working out, Twitch, how is audio quality? If I just talk for a bit, how does Twitch perceive the audio quality? No echo. Okay, that's good. And good. Okay. YouTube, how is audio quality? So I'm going to keep talking so that YouTube can evaluate the performance of my voice. And YouTube has a little bit longer delay than Twitch, but in theory, we should see it soon. Let's see if some YouTubers say that the audio is good. And Twitch, how is the video quality? Whoa, there we have all the YouTube comments. They all come in like a big batch. And then I guess while Twitch is responding whether the video is good, YouTube, how's the video now? Does the video look okay? Oh, I guess you can't actually see me. Let me fix that real quick. If I do this, I think you can now see me. Is that right? So now I think both YouTube and Twitch should be able to see my face. And you should also see Jay, I think, maybe. Yeah, of course, there's a static image. I was being stupid, but hopefully now you should see my face. And so how is the video quality now? Yeah, I know, new home. It's very weird. Hunting for exposure. Let me see if I can do something about that. Don't mind me. Is that better? Does it hunt less for exposure now? Good video on Twitch. Camera keeps trying to change brightness. Does it still keep trying to change brightness, or does it seem to now do the right thing? Nice. Great. Also, YouTube, can you see Twitch comments? Twitch, can you see YouTube comments? It seems like it given the conversation so far, but just to double check. So I'm using you all as guinea pigs for this. The light is affecting the brightness. Well, I'll try another little trick here. If I do... How's that? Is that any better? Put a little light down there. Oh, beautiful. Twitch and YouTube are interacting like nobody's business. Better. Fantastic. All right, I think we're getting close to... I think we're getting close to actually trying to run this thing. Yeah, it's a little weird to have a normal camera be the video source, because it tries really hard to keep exposure at all times. Basically, I'm using the monitor output of the camera, and so gets a little weird. Oh, that's very bright in my face. If I do, let's do that. That's nicer. What's the thesis topic? Well, you're about to find out. So I'll probably, for the actual stream, I'll probably put like a title and description and stuff. And for this, I'm just gonna try a practice run and see how you all feel about it. Am I nervous? I'm actually not nervous. I tend to not be super nervous for presentations just because I enjoy giving them. I mostly think of it as a conversation where I do a long monologue and then we can talk about things. But I have no idea what the actual defense is going to be like. Oh, do you want to hear? Let me, before we start, actually, this is a little fun. So I recently updated my camera setup, right? Okay, so I'm going to give you a side-by-side view. Watch this. Okay, so in theory, I think now you see two views of me. So I'm like on that side. I can't actually point because you see two of me. But one of them is the webcam, the old webcam, and the other. So this one is the old webcam, and this one is the new camera. Can you tell the difference? In theory, the video should be much better on one than the other. And in fact, here, let me try to switch back and forth between them. So this is the new one. This is the old one. This is the new one. This is the old one. And this is the side-by-side. It's only really when you see them that like close to each other that you really notice the difference, especially in like color tones. It's crazy. The other thing that I've noticed is the new camera is much better in low light. So hopefully this was worth it. There are people in that place. Yeah, I know, right? All right, I guess we should get started. Okay, I fixed this so I can close this and this. All right. All right, let's switch over here. And then I think in theory, so I have a new desktop or screen setup as well. So in theory, if I do this, can you now see the slide? You should see a slide that says partial state in dataflow-based materialized view. Beautiful. And me in the corner. Yeah, so I should be in the bottom right corner of the screen. And I don't know if you see my cursor, but in theory, my image should start around where I'm moving the mouse right now. Is that right? I have a little marker on my screen, and I think in theory, that's where it should be. Oh, beautiful. Okay. So now I guess we're gonna see how well this works out in practice. Okay, so to do a little bit of an intro to this, I'm giving my my thesis presentation and then my doctoral defense on Thursday, so in like not very many days. And unfortunately, because of the pandemic, it's going to be done over Zoom, but it can't be done in a public Zoom because people are dicks and they start like Zoom bombing and stuff, and the university doesn't really want that for something like a doctoral dissertation talk. And so what I decided to do was I'm going to do a presentation on Wednesday that's going to be live streamed and basically be just me giving the doctoral dissertation talk as if I was doing it on Thursday. And then I'm going to do it again on Zoom on Thursday. And then I do my defense right after the talk. And then after the defense is like a private thing. So there's a public talk that happens first on Thursday. Then there's a private dissertation like defense where I go in like a private room with the professors and they quiz me a bunch. And then I leave the room as well, virtually, of course. Then they discuss amongst themselves. And then at the end, they're basically going to give it like a yay or nay on whether I'm allowed to graduate. And they might ask for some like final edits for the thesis, but in theory, if they give a yes, I'm sort of done. I just need to fix up some things. And if they give a no, then who knows how much work I have to do. It's a little unclear. Nays are not very common, but they do happen. What I'm going to do is actually, I'm going to record both the one on Wednesday and the one on Thursday. And in theory, they'll be almost identical. And then I'll post whichever recording is better. As for today is a little bit different. I'll be running through the presentation, but I'm considering this a practice run. So the one on Wednesday I will consider like a formal run. Like I will pretend that it's the actual defense. The one today is like, I'll still be doing a talk, but there are a couple of things that might be a little like glitchy. I may not have practiced this as much as I'd like in the end. As you saw, there are a bunch of like just stream setups that might be annoying. But hopefully it should be pretty close to what will end up being presented on Wednesday. If you're only going to watch one of these, I recommend you watch the one on Wednesday or the recording rather than the one today. But today is really like focused on feedback. So I'd like you to sort of sit back and listen to the whole talk. And then at the end, like give me any feedback, questions, that kind of stuff. I'm imagining we're going to do a bunch of conversation after I'm done. I won't generally be watching the chat while I'm presenting. I'll just be focusing on the presentation. So if you have, like, feel free to chat amongst yourselves, which is unlike a normal presentation where you can't really talk. But I won't really be watching until after the presentation is finished. The presentation itself is going to be about 45 minutes. I haven't timed it exactly, but somewhere around there. And then I'll stick around for questions and feedback for quite some time after that is the plan. All right, and without further ado, I guess we should start. I also have, I have a little lavalier mic, so I'm gonna try to actually record like a high quality audio version of this, although this microphone might end up being better, I don't know yet. I just wanna make sure I actually don't lose the sound. Unfortunately, I don't have a lapel, so a lapel mic is kind of weird, but it works out. I'm a CS undergrad. Will this topic be understandable to me? That's a good question. This talk is aimed at a technical audience, but not necessarily an audience that is an expert in this particular topic. So I'll be talking about things like databases and materialized views and caches, but I don't expect you to have too much background there. I expect you to know like what a SQL query is and roughly what they look like and what different SQL keywords do, roughly what a cache is and roughly how that works. But I don't expect you to be an expert on databases or data flow or materialized views or any of that. But you'll see that as we go through the presentation. And hopefully by the end, you'll realize whether or not that's true. Like if we get to the end of the presentation and you're like, I didn't understand anything, then that's a problem, assuming you fit that rough criteria. SQL or SQL? Either, man, either. All right. There's also a little joke in this first slide, which let's see, which is, and it's very subtle. I put it there just to see whether anyone noticed. I don't know if anyone will, which is that the background image is a partially materialized view of something that was created with a flow. See, because it's a valley which was carved out by a stream over many decades, right? Centuries. And it's a view that has been materialized, has been put on paper, but it's partial because it's not complete yet. It's really dumb, but I like it. All right, let's actually do this thing. Now the next question is whether my clicker works. Yeah, it's it's definitely trying very hard, but I thought it was fun. Record. Beautiful. It's a landscape, yeah. All right. Here we go. Oh, actually, I should record this for my own personal collection, so to speak. Hi everyone, my name is John. Welcome. This is my doctoral dissertation talk, and I'll be talking to you about the work that I've been doing over the past 5 or 6 years here at MIT. And in particular, I've been working on partial state and dataflow-based materialized views. And hopefully by the end of this talk, you will understand all of those words, what they mean, and why this is something that I've decided to spend this much time on. I don't expect you to understand necessarily all of that right now. Before we start, I do want to point out that this work was supervised. I have not been working alone. I have had adults in the room. So in particular, Robert Morris, my thesis advisor, and the rest of my committee, Franz, Sam, and Malta, have been working on this with me and will be the ones who sort of make sure that this work is actually useful and interesting and valuable by the end of when my dissertation actually comes out. So let's start with why we're here. We're here because we want to make databases better. At least that's why I'm here. That's why this work happened. But in order to understand the way in which we need to make databases better and why we even need to do that in the first place, let's take a look at what databases are at some fundamental level. Well, let's do like database 101. You have some tables. In this case, let's say you have a stories table and a votes table. And if you want to query data from those tables, if you want to get some of the data that's out there, you issue a query. And the query sort of comes into the system from some application somewhere. It might do some operations on the data, like it might count records indicated by the count or sum operator here, or there might be a join that combines information from multiple sources, and ultimately some result is produced that comes back to the application. And if you want to insert data or change what's in the tables, then you just do an insert. You just do an operation directly into one of the tables, change the data in place, and then subsequent queries are going to see the result evaluated over the modified state. And this is all very well. This works really well for a lot of applications and has for a long time. But one thing you might notice from this figure is that there's a lot more orange than blue. And what that means is doing reads requires more work than doing writes. You can think of the amount of color here as sort of representing the amount of work that you have to do. And unfortunately, in a lot of applications today, and in particular web applications, you have a lot more orange going on than blue. Web applications tend to be read heavy. So they tend to issue a lot of queries, and they don't do that many changes to the data relative to the amount of reads they do. And that makes it seem a little unfortunate that the orange stuff is more expensive if it's also more common. And this problem extends beyond that, which is very often we do repeated queries that are sometimes identical or sometimes just similar. And so we end up doing this repeated unnecessary orange work where we could potentially have done a lot less just because a lot of the work is the same. And you might say, but John, what about caches? Don't caches just solve this problem? And it's true that caches do, to some extent, solve this problem. So the idea here is that you stick some storage system in front of your database, and then you have all the reads from the application go to the cache, read from the cache, so they don't need to do any work unless they miss in the cache, if the entry or result they're looking for is not cached, in which case they have to execute the query back to the database tables. And this does make queries fast in the common case. And caches really are great, but there's some other caching-like approaches, like denormalization, where you store and maintain derived values like count of votes inside other tables. But unfortunately, all of these have the problem that getting this right is really hard. So if we look at a more complete diagram of what caching looks like, it really looks something like this. Whenever you insert something into a table, your caches are now out of date. If reads kept using the cache, they would continuously get old results. And so there has to be some mechanism whereby when the data changes, we also invalidate the cache and make sure that the value that's in there somehow gets refreshed. And very often the way this works is that we evict from the cache, and then the next query that comes along does a query to the database, fetches the new updated result, and then sticks that in cache. But there are a lot of questions here once you have a design like this, and it's not always straightforward. For example, who fills in the cache? Imagine that you evict the data for some extremely popular story or post somewhere, and now like 100,000 people, which means 100,000 application requests, all come in and try to read that post immediately after because it's popular. All of them issue the query to the database, since you get this sort of thundering herd effect. But then all of them come back. Which one of them writes to the cache? Do all of them, in which case you're redoing a lot of unnecessary work, or does only one of them? And if so, how do they coordinate that? Moreover, you have this other problem of over time, if you just cache all results, if you ever miss, then now the cache is just going to keep growing without bound. And this is going to exhaust the memory on whatever machine you're running on. And so you need some mechanism for evicting from the cache over time. Of course, you have the same problem here. Who evicts from the cache and how? And this whole, the complexity of this image is the reason for my thesis. In particular, I wanted to see if there's a way to do automatic database caching. And so that's what we're going to be talking about for the rest of this talk and what most of my thesis centers around. And the way we're going to go through this talk is by looking at the title. So if you remember, the title of this talk was Partial State in Dataflow-based Materialized Views. And what we're going to do over the course of this presentation is we're going to parse that from right to left. So we're going to start with materialized views and try to explore what those mean and why they're useful in this context. So materialized views is basically a fancy way of saying, remember query results. The idea, which was invented by the database community back in like the 1980s, is essentially that you take some query and you run it, and then you remember the result from running it, so that the next time you run it, you can just use that same result, which sounds a lot like caching, and in many ways, it is similar. And the key question here, just like one of the key questions for caching, is how you maintain this materialized view, this materialization. What happens if the underlying data changes? You now have these materialized results that are out of date or stale, and you need some way to maintain them over time. Ideally, this process should be incremental, so that you don't execute the query from scratch each time. Imagine you had a query that counts the number of votes for a story, and let's say there are 1 million votes currently. If one new vote comes in, you'd like to not throw away the result and have to count to 1 million the next time someone asks. It would be better if it was incremental, if this one new vote that came in just increased the vote count by 1, because those are the semantics of a count. We also have this deeper question of, how do we maintain? Do we maintain every time the data changes? Or do we maintain sort of on demand when a read query comes in and we realize that the results are out of date? Both of these approaches are possible. You can think of these sort of as, if you maintain on write, it's sort of a push-based model. And if you maintain on read, it's sort of a pull-based model. And this question of maintenance gets us to the second part of the title, regardless of whether you go from the right or the left, which is dataflow-based. And we're going to use a system architecture called dataflow to maintain these materialized views. Essentially, we're going to use dataflow to push changes to the views. Dataflow has a number of different definitions across different fields and even different subfields of computer science. But here, the core concept of dataflow that we're going to focus on is that the data moves to the compute. You can think of this sort of as push-based computation, rather than having sort of code that goes and fetches data from the tables. We're going to have the tables send data to the different kinds of compute and have them sort of propagate changes. And in particular, the data change is going to propagate through a graph of operators, where the operators are relational operators here, like the operators you use in SQL, like joins, aggregations, filters, and other things like that. And the idea with this graph is that every edge is a data dependency. So for example, a join would depend on, have an edge to both of its inputs or all of its inputs. An aggregation would have an edge that relates it to whatever table feeds the data to that aggregation. And this might sound a little complex, so we're going to go through an example in a second. And the messages that flow over each of these edges are going to be deltas. And a delta here, you can think of as a full sort of database row that it has either a positive or a negative sign. So the idea is that if the row has a positive sign, it is an additional result to whatever query that edge represents. If it has a negative sign, it's a revocation of some past result. So you can imagine, for example, that if a count changes from 42 to 43, we would get a negative for 42 and a positive for 43. And in particular, we're going to look at data flow in the context of Noria. So Noria is an eventually consistent materialized view system that's built using data flow, and it's what all of the work in this thesis is based upon. So let's look at a particular query and a data flow just to get a feel for how this works out in practice. So here on the left, you see a particular query, and on the right, you see the data flow for that query. So here you see that the query says create materialized view, which is sort of a magical incantation to say that we want a view by the name story with VC for vote count here. And we want it to be materialized. So we want the results to be stored and maintained over time. And then you see the definition of the query. It's a fairly straightforward query. It just joins stories and votes. It aggregates all the votes for each story and stores that as a derived column votes in the output. So basically think of this as the view at the bottom produces stories with their vote count as one of the output columns. And what Noria does is it maps the query on the left to the data flow on the right. For example, the aggregation here gets to run over the votes table, right? It's aggregating the votes, and therefore it has an edge to the votes table. And you'll notice that a couple of pieces from the query are used to make this determination. In particular, we know that it's aggregating over votes because that's what's named in the count operator. We also know that it's going to group by stories.id, and we know because of the join clause that stories.id is the same as the column story ID in votes. Similarly, we know that there's a join between stories and votes, which is what causes us to add, or Noria in this case, to add the join operator that depends on both the stories table and the output of the aggregation. You'll notice here, though, that Noria has actually done a little bit of query optimization here. It's decided to do the aggregation before the join. And this is sort of a classic database query optimization problem. But in particular, either order here is allowed, and Noria has chosen to do the aggregation first. So now what happens if the application actually wants to read from this view? Well, in practice, they're going to issue a query that looks something like select all from story with VC, where the ID is, and then some parameter, like some story ID that they want the information for. And this read is going to be directed directly to the materialized view at the bottom, right? And so this is essentially going to turn into a key value lookup into that materialized view. Now let's look at what happens if the underlying data changes and how the data flow helps maintain this materialized view. So imagine that a new vote comes into the votes table. Well, Noria is going to take that right and push it into the data flow at the node that corresponds to the table it was inserted into, in this case, the votes table. And then it's going to stream that vote down through the data flow, following all of the downstream paths from each operator it passes through. And this streaming is modified by the operators that the update streams through. So as we mentioned before, when the vote hits the aggregation, it's actually going to emit a negative and a positive corresponding to that insert. So in this case, if the vote was for, say, story 7, and the count changes from 42 to 43, what we're going to emit, or what Noria is going to emit, is a tuple, in this case, of the story ID 7 and 42 as a negative delta, and 743 as a positive delta. And you can think of this as sort of a notification to downstream saying, it used to be that the result was 742, forget that output row, and instead have the output row 743. You can think of this as a replacement. And then that streams to the join, and the join's role is to emit a delta that can be applied to the materialized view downstream. So the join takes these deltas in and does lookups into the stories table to produce these complete rows. That you see there's still a negative and a positive. They still have 742 and 743, but they also include all of the columns from the stories table, which is needed in order to apply them cleanly to the rows that are in the materialized view at the bottom, because those actually contain those additional columns. And then finally, those deltas are streamed from the join into the materialized view, and the materialized view is updated. So now any subsequent read that comes in is going to see the updated row. If they try to read from story 7, they'll see that it has 43 votes, not 42. So that's roughly how Noria maintains results in response to data changes. And this brings us finally to the first part of the title and the core contribution of this thesis, which is this notion of partial state. And partial state is a little bit of a weird name, but I hope by the end of this, it'll make sense why it's called partial state. In particular, partial state is all about learning to forget. The underlying idea here is that most entries in any given view are probably not accessed. This might be because they're old and the application doesn't care about, say, story 7 anymore because it was posted 10 years ago. Or it might just be that they're super unpopular. Maybe no one reads my tweets, but everyone reads Lady Gaga's tweets. Then it doesn't really make sense to keep my tweets in memory if that causes Lady Gaga's tweets to not be in memory. The trade-off is much better in favor of keeping Lady Gaga's stuff in memory. And keeping these old and unpopular stories around wastes memory. Beyond that, it also wastes compute. Remember how we have to maintain any cached or materialized value? Well, that means that if we keep a lot of results materialized, we have to spend cycles to maintain those values as well. And it would be nice if we didn't maintain things that no one cared about. And in order to achieve this, we need to be able to evict old entries and then only add new entries on demand when the application asks for them. Basically, we need a cache that can respond to application demand as it changes over time. So there are three main contributions from this thesis. The first is to have the notion of missing state in materialized views. So this is basically what we talked about before, the ability to have some results for a given query just not be there, not be stored, and not be maintained. The second is this concept of up-queries, which we're going to look at in detail further on in the talk, which is a mechanism to populate missing state using dataflow when the application issues a query that requires that state that was previously missing. And finally, an implementation and evaluation of partial state in the Noria dataflow system. So let's look a little bit of more detail at how partial state works. So first, we need to revisit this architecture we've talked about so far for materialized views, which is that you first define a materialized view, and then you do a query over the materialized view. That works okay when you're willing to keep all the results in memory, but in our case, we're not willing to do that. But as it stands, with these two being separate, we don't have enough information to make the view partial. Basically, we don't know what keys the application is going to use to query into this view, and so we sort of don't know what key to use to mark things as missing or not. And so what we need to do as a sort of first step is we need to introduce the parameters the application is going to use into the definition of the view. So it's going to look something like this. So now when you create the materialized view, you have a where clause that basically folds in the parameter from the query that we previously had in a separate query. So here where stories ID equals question mark. And now the dataflow system can use the information about what the parameter is as sort of the index key into the state. And you can imagine here that we use this key to determine whether any given result is present or missing. So now when the application issues a query against this view, what it really does is it executes that view for a given value for the view's parameters, in this case, the story ID. And when it does this, it might miss. So here, let's say that the application executes that view with the parameter value 7 for the story ID. And that query now reaches Noria. It looks up in the materialized view, and it finds that the entry for story ID 7 is missing, indicated here by a hollow green box. Well, now the system needs to fetch the results sort of on demand and populate them so that it can actually respond with the correct result to the application. And the way this is going to happen is by having this miss trigger an upquery. And an upquery here is, you can think of it as a request for a summary of all relevant past deltas to be retransmitted through the data flow. Think of it as sort of the thing that sent the upquery says, hey, tell me about 7 again. So in this case, the upquery is sent immediately up to the next ancestor in the data flow graph. Hence the name, upquery. It goes in the opposite direction up the graph, as opposed to where data flow messages usually flow. Now, the join doesn't have any state. It doesn't have any information about 7. It's sort of a stateless operator. And so these upqueries can then recurse to trigger further upqueries into the graph. In particular, the join here might realize that, well, I don't have the state, but one of my ancestors might. And so it forwards, in some sense, this upquery to the aggregation, saying, hey, can you tell me about 7 so that I can tell this downstream thing about 7? And here we need to introduce an additional little piece of complexity, which is that so far, we've only really talked about the state that's in the tables and the states that's in the materialized views at the bottom. But in reality, there are stateful operators as well. You can think about this as, if you consider the aggregation that we talked about before, it receives one vote for 7, and then it emits a negative for 742 and a positive for 743. How does it do that? It needs to remember that the current count for 7 was 42. And what this means is that that aggregation actually has its own state. You can think of it as it sort of has a materialized view of its own output that it uses to process later updates. And this is also stored in the data flow graph. And so when the upquery that was forwarded by the join arrives at the aggregation now does a lookup into that intermediate materialized state and say that it does find that it has the state for 7. It knows that the current state for 7 is, say, 743. Well, in this case, the upquery doesn't have to recurse anymore. It has the necessary information. And so what it's going to do is it's going to forward all the results it had for 7, in this case it's just 743, along the normal data flow path back to the join. And it's crucial here that there's no need for any special operators or different forward and backward processing, which often tends to be the case in materialized view systems that want to try to do something like this. Instead, we're reusing the existing forward data flow for executing queries in order to get this on-demand compute. And the response that the aggregation sends, and indeed the response to any upquery, is just a single message that holds the current state of the source for the requested key. When this response then arrives at the join then does the same thing as it would if this was a normal data flow update. It does a lookup into stories. It produces sort of the expanded rows that has all the necessary columns for the downstream view, and it forwards that as the response to the upquery it originally received. When this state then arrives at the downstream materialized view, that fills in the state that was previously missing. And at this point, we can respond to the user query because we now have the state for story 7. And so we send that back. And what's nice about this is now the state has been populated. So if another query now comes in later, then it will be immediately fast. It will be immediately satisfied because it does a lookup in Noria for story 7. Noria finds that story 7 is already present in the materialized view, and so it just responds immediately. And what all of this enables us to do is to evict state. It lets us mark state as missing after we have populated it. So let's say that like a couple of months go by and story 7 is no longer popular. The system can decide to evict any state for 7 throughout the data flow graph. The data is still present in the base tables in case that should be necessary, in case some later query happens to want to look for 7 again, but any intermediate state we might have stored, including at the materialized views, can just go away. And thereby we've saved that memory, which can now be used for caching other stories that are currently popular. One thing that's nice about this, and you'll remember this from a while back, is that we don't want to maintain values that no one cares about anymore. And by having the state be missing, we can actually achieve that. So imagine that after evicting 7, some change happens to story 7. Imagine that its title changes or something. Well, in that case, a delta is going to flow into the data flow graph from the stories table, saying a negative for 7 with the old title and a positive for 7 with the new title. But when this goes through the join, and the join does a lookup into the state of the aggregation to produce the output results, and it finds that state is missing, it can just throw away that update, because it knows that the downstream state is also missing. If the downstream state wasn't missing, then it must have been present upstream. So because it's not present upstream, it's not present downstream, and therefore we can just get rid of the update and not have to do any more work to further process this change to 7. I want to do a bit of an intermission here and talk about related work, because now we've sort of talked about everything that the work in this thesis tries to provide you with. And so it's useful now to sort of survey the scene a little for what else is out there. So the first thing, obviously, is looking at materialized view maintenance in general. And one thing that's worthwhile pointing out here is that traditional materialized view systems target a slightly different workload than what we're going for here. They tend to target analytics workloads where, like, some analyst regularly wants to run some particularly expensive query over like some huge data set, and running that query just on demand when the analyst sits down is not feasible. It would take, say, hours to run on this warehouse analytics query. And the materialized view is basically a way to say, we know that this query is going to be issued every now and again. We know it's too expensive to run on demand, and so therefore we're just going to maintain the result always. And so the focus has really been on having support for just really high frequency, high volume writes. So making the updating of the materialized view extremely efficient. And the focus hasn't really been on reads. Reads are assumed to be very infrequent, which is not at all the case for us. We're targeting a use case where reads are very frequent. And that obviously changes the system architecture. As a result, in traditional materialized view systems, there's also usually little or no support for on-demand queries. The idea is that you like set up the system to maintain these particular views. It's not really built for just adding and removing queries and views whenever the application wishes. And similarly, there isn't really support for eviction. The idea is that the analyst knows what query they want to run, and so those are just the queries that matter. They might not even execute any sub-queries on the materialized view. Maybe they will, but in general, they're going to survey the whole materialized view each time, and so there wasn't really a need for eviction, whereas again, in our use case, it very much is. The second piece of related work that's worth looking at is automated caching systems. There are a couple of these that have come both out of industry and out of academia. Unfortunately, few of these are general purpose. Many of them are built by large companies that just had a particular problem in their deployment with using, say, MySQL and Memcache, and they built this sort of elaborate protocol or system to make sure that everything was up to date. But these aren't really intended for you to just download and run for your own application. They're built very much for the particular deployment that company had in mind. Many of them also don't really support updating, like incrementally updating the materialized views or the caches. Instead, they're usually focused on being able to correctly invalidate results and fill them up as needed when clients miss in the cache. But this, of course, is unfortunate when you have queries that might actually be somewhat expensive to execute, and you want to avoid re-executing them whenever you can and just maintain them incrementally. And finally, many of these systems are limited to specific database interactions, often through a framework or an ORM or something like that. And they're not really targeting just general purpose SQL, which is what Noria is built for. The idea is that the application already uses SQL, and we're just going to leverage the fact that we know the semantics of the SQL query. And so we support just sort of the arbitrary SQL that the application gives us. And finally, and especially in recent years, there's been a lot of work on data flow and stream processing systems. And these two are usually focused on write performance. The idea is you have this huge data pipeline and you want to process a bunch of queries over it. And reads happen, but they're usually much more infrequent. They're for sampling analytics, for example, over the whole data stream, rather than application queries that are just being issued at a much faster rate than the writes. They also tend to focus on strong consistency, and usually this comes at the cost of read latency. The reads in these systems very often have to pass through the write pipeline of the system in order to ensure that the result that comes out reflects all of the writes that have happened so far exactly with some well-defined semantics. Whereas in Noria, we leverage the fact that we're allowed to give slightly stale results in order to significantly improve the read latency. And like the systems before, most of these systems have limited or no support for on-demand computation or for eviction. The idea here is if you have a new materialized view, you have to like spin up another data flow. If you want to evict, well, you terminate the process. You can't really remove stuff from the materialized views once they've been set up. So the question now arises, well, now that we've looked at this and Noria provides all these nice things, are we done? Is there nothing more to be said? And of course, that's not true, because if it was, this thesis would not really be that valuable. And so it turns out that just in practice, things are hard. We have, in particular, to ensure that data changes take effect exactly once. And what I mean by that is if you do an insert into a table, you need to make sure that that insert, well, happens, so it can't be applied 0 times, but it also can't be applied multiple times. Like the insert, like inserts 3 duplicates of the same row or something. That would obviously not be okay. And traditionally, this is easy. If you think of any existing database, the only way in which you would have a row not be reflected or be reflected multiple times is if the database had a bug in it. But in this data flow world, the model becomes a lot harder, especially in the presence of upqueries. And this is because these upqueries hold past state, right? You can think of them sort of as snapshots that hold a bunch of deltas that have been applied in the past. But there are concurrent updates to the data flow. Like imagine that someone does an upquery for story 7 at the same time as story 7 is being updated. And now we have these 2 data flow messages that both contain, or one or the other contains, some particular delta. And we need to make sure that every change that happened at the top from the application is reflected only exactly once. It also gets challenging because, as I mentioned, we have this idea of we want to be able to not spend compute on maintaining results that are no longer present. And so sometimes we drop updates because we think that they're not relevant to the downstream data flow. There's nothing for them to update. But if we do this incorrectly, if the logic there is wrong, we might end up discarding an update that actually would have made some downstream state be up to date. And discarding it means that downstream state is now permanently stale. So there are a lot of hazards that come up in this sort of totally asynchronous world, but I don't have the time to actually talk through all of them in this presentation. So instead, we're going to focus on a particular one. And if you want to read about some of the others, I suggest you go read my thesis when it's eventually out. In particular, we're going to be looking at incongruent join evictions. Now, if you don't know what these are, that's not terribly surprising because it's a word that I made up. But I do think it's a fairly accurate term for what happens. So let's first then look at what is an incongruent join. So here, I'm giving you another query and data flow slide, but the query and the data flow here are different from the ones that we looked at before. In particular, here, the query is a little simpler. We have a stories table like before, and we have a users table. And the idea here is that every story has an author, and every author is a user. So in the stories table, we just store sort of an author ID. And then what we want in the materialized view at the bottom is just to perform the join with users so that we can print the author name when we print the story and not just the author ID, which would be useless to users. So just a straight up join between stories and users on the author ID. And then we want to be able to look up into the view based on the story ID. And this is what makes this join incongruent, is that the query key is not the same as the join key. Right? The query key is the identifier of the story. The join key is the author ID of the story, and these two are not the same column. And you might wonder, well, why does this matter? So let's actually walk through an example. It turns out this is fine for up queries. Imagine here that an up query comes from, again, story 7. It gets sent to the join. The join is stateless, so it forwards the up query, say, to stories this time. Stories then replays the result for 7 and says the author is author number 42. And now the join needs to do lookups into the other side, into users. So it does that lookup. It finds that author number 42 has the name Lena. And so it returns along the data flow. It returns to the lookup that information. The join then produces a downstream story that or downstream delta that says story 7, the other columns from stories, and the author name is Lena. So far, so good. But remember this figure, right? Where we were discarding an update because we missed when we did a lookup into the join while processing just a normal data flow message. And that causes some problems in this particular case. So let's imagine a case where the author changes here. So the way this is going to manifest is the stories table is going to produce a delta that has a negative for the old author ID and a positive for the new author ID for story 7. That gets forwarded down to the join. And then the join has to propagate these changes into the view. But the view holds the author name. So the join needs to perform the join in order to make the deltas match up to the downstream state. So it does the same thing. It does a lookup for 42 into users, finds the name Lena, updates the delta to include that additional column from the join, and then moves on to the positive, where it now has author 43. But now imagine that the lookup for 43 into users misses. The state for 43 is not known. Now, a quick aside here, you might wonder, how could this happen if users is a table? How could anything ever be missing from there? There are a couple of answers to that. For example, you could imagine that the users table is stored on disk and that particular user is not in memory, and we want to represent that with upqueries. That's not something Noria currently does, but you could imagine it worked that way. The more realistic answer is that what I'm giving you is sort of a simplified data flow graph. In practice, users doesn't have to be a table here. You could imagine that users is just the end result of some complex query that has data flow going far up above it. And therefore, there could totally be missing state in that view. Ultimately, though, what matters is that we can't finish processing this delta because we don't have the author name to include in the positive part of the delta. So what do we do? Well, we can't produce the needed update because we don't have the state. We can't forward just the negative because if we did, then any subsequent query for story 7 would end up with an empty result set, which is of course not correct. There is a row for 7. We just don't know the author name. We can't drop the update altogether either, because then any read from the downstream materialized view would get a permanently stale result, which is also not okay. We need to make sure that at some point this change gets reflected. Think of this as having to apply the exactly once rule to the change that changed the author name. Well, author ID rather. So you might think, well, why don't we just fill in the missing state? Like, what's the big problem, right? Why don't we just do that? Well, it turns out that this gets pretty challenging. If you try to fill this state, then while we're waiting for that state to be filled, the join cannot process any more data flow messages because it's currently in the middle of processing this update. If a later update comes along, that update might depend on the one that we're currently processing. Like imagine the author changes again. The negative in that needs to match the positive that we previously emitted, but we haven't emitted it yet. So we can't just continue processing in the join. So the join has to pause, which means that we're pausing processing of all writes that arrive in the data flow going down to that join. And filling the state might take a really long time. Who knows how complex the data flow is above the table on the right, or how slow the disk is. And it turns out it's even worse than this. And the thesis describes this a little bit further. You can actually end up in deadlock situations where the join can't process any more messages, but the join has to process more messages in order for the missing state to be filled. And obviously, this is a problem. So it turns out filling the state is not straightforward. So we have to scratch that idea. So then the question becomes, well, what do we do? It turns out that we actually already have the mechanism, which is eviction. Partial state gives us a mechanism that lets us solve this very problem using its own mechanisms. In particular, what we can do is we can just evict story 7 downstream. It's true, we don't know how to update it, but we can just say, state 7 is just invalid now. You have to recompute it if you ever want to read again. And this works because now if any subsequent read comes in for story 7, it's going to go through the normal upquery path. And as we saw, that actually produces the right answer. And the same thing would happen here. The upqueries would cascade until they actually find the state on both sides. And at that point, it would actually compute. So now we've gone through one of the problematic cases. As mentioned, there are a number of other ones, but the thesis gives solutions for those. And so the question now becomes, well, does this work? Like we've built the system, does it actually provide any value? And in order to find the answer to that, I need a realistic test subject. And so what I decided to do was to look at lobsters. If you're not familiar with lobsters, it's sort of a Hacker News-like news aggregator where their users can submit stories and then the users vote for and comment on those stories. You can see sort of the most popular stories, a very traditional website setup these days. And I chose lobsters because it's open source, so we can see all the SQL queries that it issues, but also data statistics are available for the particular workload that lobsters sees. Things like how popular are different stories to one another, how active are different users compared to one another, which pages are most frequently accessed, that sort of stuff. And using this information, I was able to build a workload generator that synthesizes lobsters-like page requests. And then I built an adapter for different backends like MySQL and Noria that produces the SQL queries that the original application produced with the same sort of data and value distributions. And then it interacts directly with whatever that backend is. So rather than going through the Ruby on Rails code, which would be pretty slow, it just directly issues database queries. But it ends up doing the same work that the real database or the real website would have done. And so let's look at how that actually performs. So this is showing a throughput graph. So the y-axis here is the number of pages per second that the system can support. And the graph on the far right here is MySQL. This is about 500 pages per second. This is on an EC2 instance with 16 cores and 128 gigabytes. And it's showing the page throughput across all the different page requests that might be issued. And here, MySQL is CPU bound. It can't get above 500 pages per second just because it's saturating all the 16 cores on the server. And notice that this is actually with a denormalized schema. The Lobsters developers have already done a bunch of work to have these additional columns to speed up lookups. They have something that's sort of similar to the vote count that we've looked at before, where it would be too expensive to count the number of votes and comments and stuff for each story on every page request. So they actually keep like a column in the stories table called hotness that tracks how hot a story is over time, and they update it anytime a comment or vote or whatever comes in. Without this denormalization, this manual optimization, MySQL cannot even do a single page per second. So now let's see what happens if we run Noria. So this is going to be Noria without partial state. Noria without partial state does significantly better. This is about an order of magnitude faster than MySQL. And this, of course, shows you the power of materialized views or of caches, however you want to think about it, that here we're using the memory to speed up the reads. The reads no longer need to execute queries, so they execute very quickly. And since most requests are reads, everything is faster. Unfortunately, here what happens is we run out of memory. This machine is 128 gigs of memory, and we use all of it for the materialized views. And this is a version of Noria that already only materializes the values that the application has asked for. If the application never issues a particular query, it won't be materialized. But it just falls over entirely. It's not CPU bound, it's memory bound by the size of memory. And then let's look at Noria with partial state. So with partial state, Noria does significantly better. It does gets about 67% higher performance than Noria without partial, and about 18 times that of MySQL. And here, it doesn't even run out of memory. What happens is that it falls over due to upquery processing on a particularly update-heavy path that exists in the Lobsters application. And it could be that with some optimization to that update path, we could scale even further. There are plenty of free cores, and there's plenty of free memory on the server at this point. So we're bottlenecked by single core performance for upquery processing. We can also look at memory use here specifically. So here, this is running at the highest load factor that Noria without partial could run at, and then we're looking at Noria with and without partial. So without partial is on the right, and with partial is on the left. And you see that Noria with partial uses significantly less memory than Noria does without partial. Noria also, by default, has all the base tables stored in memory, which of course means that the memory imprint is very large. And this is sort of unfair to partial, because partial can't evict from the base tables, as we talked about before. But Noria does have a mode where the base tables can be stored on disk instead. And if we enable that, we see that the memory save is actually even further. So here, Noria with partial uses about 1/3 of the memory of Noria without partial. The other thing you might wonder is, how does Noria measure up against, like, if I already implemented my own caching system using memcached or Redis or something, like, is Noria really going to perform as well as that? And it's a really hard question to answer, because it really depends on how you implemented the caching, like the exact caching logic and caching mechanisms you used. But what I did was I ran an experiment where I tried to construct essentially an idealized caching setup. So what I did was I ran just not full Lobsters, because it would be too hard to actually measure anything useful there, but just the query we looked at before, the stories and vote count query. I ran that against Noria and against Redis in a setup where there are no cache misses. So you never have to go to the database. So only Redis is ever involved. Almost everything is reads, so there are no invalidations. And the workload is extremely skewed, so that some keys are much more popular than others. And then I ran this system against Redis and against Noria, and just looked at what is the overall throughput that could be achieved. Is that what you can see here? This is running directly against Redis. And the line on the left, the sort of dashed line for Redis, is the performance that Redis achieves. And this graph is a little weird. It has latency on the y-axis and throughput on the x-axis. And what you end up getting is this is sort of how well the system performed, and the offered load to the system increases along the line. And so what you end up with is, as the system stops keeping up, the latency goes up, but the achieved throughput does not. And so you get this hockey stick effect when the system no longer keeps up. And you see that Redis here falls over around 1 million requests per second. Now, Redis is single-threaded, so this is a little unfair to Redis. And so I've also plotted 16 times that value. Remember that the server that we're running on here has 16 cores. So this is sort of the best you could possibly do in a manual caching setup. Like, every read is a single key lookup. And then I ran Noria with the same workload. And remember, Noria has full support for SQL. There's like all the cache updates and everything like that is handled. And Noria actually does pretty well. It falls over around 9 million requests per second. It gets to about 2/3 of this sort of hypothetical highest Redis performance on this server. And this suggests that even against a manually tuned caching setup, Noria is likely to do pretty well. So we're getting towards the end, and I'd like to wrap things up a little. First, by talking just briefly about future work. Noria is neither perfect nor complete. There are a number of things that haven't yet been implemented that probably should, like range queries and cursors and timed window operators. It'd be nice if Noria could support having the base tables be stored in existing databases upstream, or if Noria's deltas could propagate all the way down to views that are stored on client devices like phones and automatically maintain views that are kept there. Also, Noria doesn't have the greatest fault tolerance story, and Partial might be able to help with that by using Partial to repopulate state if a node goes down. I also want to acknowledge a few people who have made it possible for me to get to this stage. Obviously, first, my committee has helped enormously, especially Robert and Franz, who have been my advisors on this project for the past 5 years and have like continuously been asking questions of me and sort of pushing me on trying to build a better story for Noria and what it's for and how it works. And Malte Schwarzkopf, who was a postdoc in my group during most of the work on Noria. He's the reason why Noria supports SQL in the first place and has done a lot of query optimization work, for example, and Noria would not exist without his help. And of course, Sam for being like the database voice of reason in the room. And I'm sure that in the defense later, he will have many questions. I also want to thank my group at MIT, the Parallel and Distributed Operating Systems group. The people there have endless curiosity and insight and support that I think has been invaluable in making me who I am and being able to build this in the first place. My family, both my parents and step-parents, who have always been encouraging me to pursue my interest, no matter how geeky they might be. And I think without them sort of nudging me along, I wouldn't have ended up doing something quite as nerdy as this. And my girlfriend, Talia, who I'm amazed has been supporting me through all of this and especially tolerated when I've locked myself in my room for hours on end trying to just get this thing finished. And I love her. So to conclude, my thesis enables materialized views to be used as caches. It does so by allowing state to be missing from materializations and using upqueries to populate missing state on demand. The resulting system provides automated caching for SQL queries and reduces the need for complex ad hoc caching logic. Thank you for listening and watching, and please ask any questions you might have. Thank you. All right. That's my talk, 52 minutes, so a little bit too long. All right. Now that we're all the way through, let's, I saw the to-do that the camera blocks. I have a little thing that shows where my camera is, and I see it blocks some stuff on certain slides. Apart from that, though, how do you feel? Was it possible to follow? Very understandable. That's good. I'm glad. If my committee lets me pass without corrections, I'd be very surprised. But, we'll see. The cache icon is the same as the tables. That's true. I consider not doing that, but the reason I kept them the same is because they sort of are the same as far as Noria is concerned. Like, all that matters is that they're materialized, and base tables can be materialized as well. Definitely followable. That's what I wanted to hear. I think it was easier to follow this presentation than earlier streams you did. That's not terribly surprising. The earlier streams were very detailed, like the evaluation walkthrough, for example. And this one, of course, is structured as a presentation with like diagrams and stuff. And so it was intended to be easier to follow. Only joined for the last 10 minutes, but this was still easily understandable with the things I picked up from earlier streams. That's good. How long do you reckon you'll spend on corrections? It really depends. I honestly don't. Oh, wait, I should stop. Stop the audio recording. How long do you reckon you'll spend on corrections? It's a good question. It's really up to the committee. The committee could request very few or surface level changes, or they could like require me to change everything. I honestly don't know. If they ask me to like redo evaluations or experiments, for example, that tends to take a lot more time than just text editing. I'll only be taking questions at the end, not throughout, for the actual presentation. Same like now. At some point it got difficult to follow, not for the topic depth, but the length. Yeah, I mean, this is how long thesis presentations are. They're generally 45 minutes. This one did run a little bit over, and so I need to figure out how to cut some things. I'm not quite sure what yet. Names on the colleague photos would be okay, just a thought. They're already named on the second slide. The committee is specifically named there. I could name them again here. The hockey stick graph is a bit hard to grasp. Yeah, it's the hockey stick graph is like, it's pretty standard in some areas of computer science, and explaining it and how to read it in a presentation where I have this little time to talk about it is pretty hard. I don't really know of a better way to visualize the same thing. I could just have it be bar graphs, and just the latency is arguably not that important. So maybe that's what I should do. Only thought that in the beginning when you were talking about colors, it got a little confusing with regards to what the colors represented. And that's me really trying hard to find things to nitpick about. Well, it's funny because the colors throughout the presentations are actually very specifically chosen. Orange is always reads and things related to materialized views. Blue is always writes and things related to updates and data flow. And green is always things that are related to partial and eviction. How does Noria support non-abelian aggregate functions like min-max without having to keep a large set of values for a single key in memory in order to support deletes? So this is where I mentioned that there are a couple of things that Noria doesn't really support yet. And one of them is ordered collections, which is one way to get around this. When you have things like a min and max, if you don't have an ordered index, you're sort of forced to keep all the state anyway. So in these cases, Noria will just require, like basically disable partial state for that view, because there just isn't a way you could maintain it partially. One question I did have was between, actually, let me, like this. One question I did have was between your two slides for the different stories queries, join on votes and join on users. If the where stories ID equals 7 is used for both queries, how does Noria determine whether it needs to perform an up query? Well, the two queries are different, so they represent different materialized views. And so a query for 7 on one and a query for 7 on the other, they're queries to different views. And like the query is different, and therefore the query has a different internal name, and so they get routed differently. 6 years to 50 minutes. Yeah, it's super weird. Sorry, I'm trailing behind chat a little bit. I didn't know a thing about materialized views, and I understood everything here, so really nice. That's good. It might suggest that it's not technical enough. I'm not sure. Still need to figure that out. I'm trying to sort Noria into existing solution styles. It looks like an eagerly populated data template. That much is obvious. How is data organized, implemented in the backend? Tables as well. Internally, Noria does store the tables as just like they're basically hash maps with a bunch of indices on it. I don't know what you mean by data template, but it really is a data flow system internally that happens to look like a materialized view database, is the way to think about it. In the chart slides at the end, there's a short green line below the chart that's confusing. Yeah, that one's there just because of the Google slide template, and it's annoying. I agree. Do you have slide numbers? I do not. That's a good point. Arguably, I should write some of this down. I also have backup slides. Let's see. All right, so what did we say? Hockey stick maybe turn into bar graph. Slide numbers. I feel like the talk is very approachable, but not sure whether the committee will be happy with it. For example, you might want to explain the details of the experiments. So keep in mind that the presentation is not really for the committee. The presentation is for a wider audience. The committee reads the thesis, and that's what the defense is based on. Like, it's not even required that you give a talk for your defense. Will the thesis be available publicly? Yes, I will make it public. The details of the experiment I also think are relatively not that important in this particular presentation. There are obviously a lot more details in the thesis. Have you compared to other databases beside MySQL, Postgres, for example? The OSDI paper from 2018 compares to a couple of other databases. Generally doesn't matter. Like, all the databases are slow at this because they have to do compute and we don't. So it'll still be an order of magnitude difference. I'd be interested to see comparisons to existing incremental materialized view implementations in databases. There aren't really that many. As I mentioned, the only ones that really exist are things built for analytics queries. Like, one of the biggest ones recently is a paper called a system called DB Toaster. It doesn't support reads. The only way you do reads is you have to, like, first of all, the entire thing is compiled, so you can't add queries on demand. That's just not supported. And the way you get reads out is you have to, like, stop processing of writes and, like, clone the whole materialized view. It's really not great. Might consider red for eviction. I'm not using red because of red-green colorblind. Well, I'm not, but I know many people are. So the three colors of the presentations, the green and the blue and the orange, are all distinct for most colorblind people and also in black and white. What's the purpose of a negative update? Wouldn't that mean that the old value have to be stored in multiple places in the view and also the aggregates? So the negative update is not stored. The updates are just forwarded along the edges. So when a negative update is applied to a view, what's stored in the view or the negative is not stored in the view. The negative causes a given row to be erased from the view. A bit odd on, like, query from applications versus inserts into the table when inserts are also queries and from the application. So yeah, I use queries to talk about selects and inserts to talk about insert, update, delete, which maybe is confusing, but I really wouldn't think of inserts as queries because they don't query for anything. You're right that they are both from the application. I don't really have a better word to use there. Like, I could use reads, but that understates the fact that the application actually does a query, not just like a read sort of implies a key value lookup, at least to me. What are corrections? Corrections is I submit a thesis to my committee, and the committee then reads through the thesis. I have my defense, and then they might go, here are a bunch of things that we want you to change before you're done. Before this is in a state where you can sort of publish it in a sense, or basically before we'll sign it. And those are corrections. Are you planning to keep working on Noria or other databases after your PhD? Not really. I think I need a break. Not because I don't think they're important or good, but just because they've been consuming my brain for so long. How much background information can you expect from your audience? If they are largely database people, I would try to speed up and go a little more in detail. They're not necessarily database people. You should think of these as, like, people at MIT who are computer science people, but not necessarily database people. Should the comparisons include the hardware specs when you say fixed resources? I say the hardware specs, as you noted. I don't think it's necessary to also have it on the slide because it doesn't really matter. What matters is that the two graphs have this, or the three bars have the same available resources, and it doesn't really matter what those resources are. As someone who works on big data SQL query processing engines for a living, I thought the talk was on the right level, easy to follow yet still interesting. I have read your paper before though. Okay, good. That makes me feel better. How does Noria compare to differential data flow and materialize? So I got at this a little bit in the related work. I just didn't name systems specifically, which is differential data flow, and in particular its implementation in materialize, is still very focused on write processing and strong consistency. And so the read processing there is much slower than in Noria because the reads have to go through the data flow. And the consistency ends up costing them. Although, of course, the benefit is you get stronger consistency. And also, there's no story there for eviction, which is obviously the core of this work. If data is stored in this manner, it sort of looks like a graph nodes internally. How much performance can we expect for GraphDB style views that are not pre-cached? So it's important that even though the data flow is even though the materialized views are maintained by a graph of operators, you should not think of these as graph queries. Those are very different things. The graph implements a relational query, not a graph query. In order to support graph queries, you need to support things like loops in the data flow, which Noria does not. For that, you need something like differential data flow, which explicitly has support for that. On GitHub, it looks like you're pretty much the only active contributor to Noria. What's the future of the project once you leave? A little uncertain so far, but like there are a number of other people who are working on smaller avenues for going forward with Noria, and I don't know exactly how those are going to pan out. The Lady Gaga reference was particularly specific as opposed to a celebrity. Not sure if that was intentional to show personality or not. No, that was just to choose a celebrity that people knew was a celebrity, really. And because Lady Gaga has come up in some papers in the past of just having like the skew. You get this like really high data point, but it doesn't really matter. I'll add it to the note. You mentioned that Noria is eventually consistent. Does that mean that reads do not support snapshot isolation guarantees, meaning it's possible to read partial or uncommitted writes? Yes, that is what it reads. You can see stale results. You can see updates being partially applied in Noria. That is certainly true. Okay, so the notes I have so far are the hockey stick should maybe be turned into a bar graph or have an explanation of what is good and what is bad. Slide numbers and use a celebrity instead of Lady Gaga. Are there other notes that you have that I should have written down and didn't? In what software was the presentation made in? It was made in Google Slides, although I tweaked the template a bunch. I don't remember, but do you talk about eviction strategies? I don't talk about eviction strategies in the talk, although it is in the thesis. Noria's eviction strategy is currently pretty uninteresting. It just does randomized eviction. And this is because randomized eviction does not require coordination between the data flow and the reads, which speeds up the reads. But there are a bunch of ways in which you might be able to get smarter eviction in Noria too. How do we evict from all the operators consistently? So this is another thing that's covered in the thesis, which is basically you have to evict downstream whenever you evict upstream to ensure this property of if state is missing in a sibling, then it's also missing downstream. Are there real numbers on Redis concurrency instead of just theoretical? Redis does not support concurrency. It's single threaded. So there isn't a way to get like the 16 core number. We could do it with memcached, but memcached is slower in part because it supports concurrency. And so like the 16 times Redis is my way of getting at the best number I know how to get at. Do you think writing an OS in Rust can be a PhD thesis? Maybe. Writing an OS in Go was a PhD thesis out of my group like last year. So writing one in Rust seems like maybe it could be. I think there already are some. Slide numbers should be in the notes too. Well, what do you mean in the notes? Where can we see the presentation? Just got here a few minutes ago. Well, I think the live stream is recorded on Twitch for like 7 days or something, so you can always go back and watch it there. But the actual presentation is going to be on Wednesday. the one that's going to be public and live streamed. And my guess is, like, certainly based on the response here, my guess is that the presentation on Wednesday will be fairly similar to this one. That's my guess, at least, because it seems like this went pretty well. Was Rust an ideal language for Noria or not necessary? I don't think Rust was necessary for Noria. I think Rust was a very good fit for the kind of things that Noria cares about. For example, it has a lot of concurrency internally, and managing that concurrency was pretty easy in Rust. There are a number of places where we wanted extremely low latency for things like reads, and the being able to fiddle with memory the way you can in Rust helped a lot there. Does the thesis include strategies for transaction rollbacks? Noria does not have transactions, so no. All right, I think then that's all. Thank you everyone for coming out. I was not expecting like 200 people to watch the practice talk, but I'm glad you all watched. It seems like in general it was possible to follow and interesting. I hope I see some of you on Wednesday. Again, the Wednesday will probably be fairly similar to this given the feedback, but if you want to watch both or you want to hear it again, then go ahead. Thanks, everyone. I will see you on Wednesday. Bye.